Next important topic is hypothesis testing. Data scientists and statisticians are often faced with yes-no questions. For example, is chocolate good for you? Talking about contaminated product, water or chicken or any other product. Answering questions about demographic of different states or populations. Whether we answer questions like this depend on the data we have. For example, when it comes to demographic, we like to use census. For contaminated product or something like water, we need experts to collect data and measure the contamination. Whether the chocolate or any treatment is good for you, well, we need medical experts to make the decision about that. How do we assess a model? In data science, a model is a set of assumptions about data. Often models include assumptions about chance processes used to generate data itself. Sometimes data scientists have to decide whether or not a model is good or not. In this section, we will discuss an example of making such decision. Our topic of focus is jury selection. Data science can be a powerful tool for exposing racism and inequality in our society. This section is about a case where data provided evidence of racial bias in jury selection. Amendment 6 of the United States Constitution states that in all criminal prosecutions, the accused shall enjoy the right to a speedy and public trial and an impartial jury. Well, how do you select the jury from a population? Is this bias processed or not? One characteristic of an impartial jury is that it should be selected from a jury panel that is representative of the population of the relevant region. A jury panel is a group of people chosen to be prospective jurors. In the final trial, jury is selected from among them by deliberate inclusion or exclusion, and as a result, can have any composition. But the large panel from which the trial jurors are drawn must be representative of the population itself. So the question is how this process is done. Is it random? Is it biased? The question of whether a jury panel is indeed representative of a region's population has an important legal implication. If some group in the population was symmetrically underrepresentative on the jury panel, that could raise question about if the jury was impartial and hence whether the defendant received due process. That was the question in the Supreme Court case of Robert Swain, a Black man convicted in Talladega County in Alabama in 1962. He appealed his indictment all the way to the United States Supreme Court on the grounds that the Black population were symmetrically excluded from juries in Talladega. The Supreme Court denied his appeal, and Robert Swain was later sentenced to life imprisonment. However, our analysis below shows that the data are not in agreement with conclusions drawn by the court. On the contrary, the data point to bias in the jury selection process. This bias in the criminal justice system reflected the widespread prejudice and injustice prevalent against Black people at that time. So we're going to start by looking at the numerical details. At the time of trial, only men aged 21 or more were eligible to serve on juries in Talladega County. In that population, 26% of the men were Black. As is common in jury trials, the jurors in the trial of Robert Swain were selected from a panel of people who were supposed to be representative of the population of eligible jurors. But only 8 men among the panel of 100 men, which is about 8%, were Black. As part of his appeal, Robert Swain questioned this discrepancy. Moreover, he pointed out that the Talladega County jury panels for the past 10 years had contained only a small percent of Black panelists. The U.S. Supreme Court reviewed the appeal and concluded that the overall percentage discrepancy has been small. But was this assertion reasonable? If jury panelists were selected at random from the county's eligible population, there would be some chance variation. We wouldn't get exactly 26 Black panelists on every 100% panel, but would we expect a few as 8? So our goal is to answer this question and analyze the data. The answer that there is no. We will establish that and then discuss some of the many biases involved. A model of random selection. One view of the data, which is a model in other words, is that the panel was selected at random and ended up with a small number of Black panelists just due to chance. Since the panel was supposed to resemble the population of all eligible jurors, the model of random selection is important to assess. Let's see if it stands up to scrutiny. The model specifies the details of a chance process. It says the data are like a random sample from a population in which 26% of the people are Black. We are in a good position to assess this model for the following reasons. First of all, we can simulate data based on the model. That is, we can simulate drawing at random from a population of whom 26% are Black. Our simulation will show that a panel would be like if it were selected at random. We can then compare the result of the simulation with the composition of an actual jury panel. If the results of our simulation are not consistent with the composition of the panel in the trial, that will be an evidence against the model of random selection. Therefore, it will be an evidence against the fairness of the trial. Very good. To simulate one value of the statistic for the proportion of Black jurors in a randomly selected panel, you can use sample underscore proportion function with the specific parameter. Here's how you can implement this simulation. First of all, import NumPy as NP and define a function to sample proportion based on given probabilities. I define a function, pass in 2 arguments, define categories, Black, non-Black, and then sample from the categories based on the specified proportions. We're going to take sample of size 100. The proportion for Black and non-Black based on the information given to us is 26% and 74%. Now, simulate one value of the statistic, which is the proportion of Black jurors. We're basically using our function to do that, and then calculate the proportion of Black jurors in the sample. So NP sum and pass in sample underscore proportion underscore Black and compare it with Black, and then divide it by the sample size to get the proportion. Let us run the simulation a few times to observe variations. For underscore I in range 5, set sample underscore proportions, the sample size and eligible population, to be sample underscore proportion underscore Black, and then add all of those together. This loop runs the simulation multiple times to show how the proportion can vary. Simulating multiple values of the statistic. The focus of our analysis is the variability in the counts. Suppose we want to generate 10,000 simulated values of the count and see how they vary. As usual, we'll do this by using a for loop. Import numpy as np, define the function as we did before, just repeating what we did before, and then take sample size of 100, and the function to simulate one count of Black panelists. Let us add the repetition to be at 10,000, and let us define a for loop for I in range of the repetitions that we are setting to be 10,000. It counts and then append simulated counts to the array. We can take a look at the result as well. The histogram shows that the center is about here. This is count in a random sample and the percent per unit. This is just simulating multiple values of the statistic. Now, let us compare the prediction and the data. In the panel selected from the trial, there were 8 Black panelists. The histogram of simulated count is redrawn below with value 8 shown as a red dot on the horizontal axis. You're going to see that this is an outlier. Very few of the 10,000 counts simulated by random selection came out to be 8 or less. So by running the line of code, we define the function, and then here we are doing the repetition, the number of repetition to be 10,000, and we define our for loop. And let us take a look at our histogram. And basically, you actually see the red dot, which is far away from the majority of the data, which is on the right-hand side. So it is an outlier. Now, let's talk about multiple categories. So far, we had just a population, and we took random samples from that population. Whether jury panels are representative of the eligible population continues to be an important question. We will address it in the context of more recent panels than that of Robert Swain in 1960s. The general process of assessment will be the same as before, but this time we will consider panelists in multiple racial and ethnic categories, not just 2. For a technical perspective, this means that we have to come up with a new statistic to simulate. Once we have simulated it and arrived at the conclusion, we'll examine some of the underlying causes of the discrepancies that we observe. Jury selection in Alameda County. In 2010, the American Civil Liberties Union, ACLU, of Northern California presented a report on a jury selection in Alameda County, California. The report concluded that certain racial and ethnic groups are underrepresented. So, we want to know if this is a bias or it was just a random selection. As you saw in previous section, trial jurors are selected from a larger jury panel. By law, the jury panel is supposed to be representative of population of eligible jurors. In California, the word representative is clearly defined as selected at random. Section 197 of California Code of Civil Procedure says that all persons selected for jury service shall be selected at random from a source or source inclusive of representative cross-section of the population of area served by the court. Here, selected for jury service means being selected to be on the jury panel. Okay. Now, for the composition of panels in Alameda County, let us focus on the study by the ACLU of Northern California, which was the racial and ethnic composition of jury panels in Alameda County. The ACLU compiled data on the composition of the jury panels in 11 felony trials in Alameda County in years 2009 and 2010. In those panels, the total number of people who reported for jury service was 1,453. The ACLU gathered demographic data on all of these prospective jurors and compared those data with the composition of all eligible jurors in the county. The data are tabulated below in a table called jury. In each category, the first numerical value is the proportion of all eligible jury candidates in the category. The second value is the proportion of people in the category among those who appeared for the process of selection in the jury. The labels for the different categories I taken from ACLU report, which says the category Other includes people who identify as mixed race without identifying one primary racial identity and individuals who didn't identify a race or ethnicity. The label Asian PI means Asian or Pacific Islander. The label Black AA means Black or African Americans. Very good. So from data science library, let us import table and also make array. Our goal is to create a table. In our table, you're going to see you have three columns: the ethnicity, eligible, and the panels. Here you have 15% Asian / PI. In the panel, you have 26%. Black or African American, 18%, and it decreased to 8%. Caucasian, 54%, and it's the same, 54%. Hispanic, 12%, it decreased to 8%. Other, which is just 1%, and now it increases to 4%. Some ethnicities are overrepresented, and some are underrepresented on the jury panel in the study. In particular, panelists in the Black, African American, and Hispanic categories are underrepresented. Very good. Now let us take a look at our bar graph, bar chart, which is basically showing the ethnicity, and you can easily compare these together. The blue one is the eligible ones, and the yellow is in the panels. So you can basically see that for Asian, it increased. For Black, African American, it decreased. Caucasian stayed the same. And then Hispanic, you have a decrease. And for other, you have an increase. So let us compare with panels selected at random. What if we select a random sample of 1,453 people from the population of eligible jurors? Will the distribution of their ethnicities look like the distribution of the panel above? There's a technical note here. Random samples of prospective jurors would be selected without replacement. However, when the size of a sample is small relative to the size of the population, sampling without replacement is similar to sampling with replacement. The proportions in the population don't change much between draws. The population of eligible jurors in Alameda County is over 1 million. And compared to that, a sample size of about 1,500 is quite small. So we're going to sample with replacement. In the cell below, we sample at random 1,453 times from the distribution of eligible jurors and display the distribution of a random sample along with the distributions of the eligible jurors and the panel in the data. Very good. So now take a look. What do we have here? The distribution of random sample is quite close to the distribution of eligible proportion for the population that we saw. So for the ethnicity, Asian Pacific Islander, the eligible was 15%, the panel was 26%, and now when you take a random sample, it's going to be about 16%. For Black African American, it was 18%, the panel is 8%, and now for the random sample, you get about 19%. For Caucasian, all of these numbers are almost similar. For Hispanic, it was 12%. It decreased to 8%, but when you're looking at the random sample, it's about 11%. And for other, it was 1%. It increased to 4%. And then when we look at the random sample, it is about 1% again. So let us take a look at the next line of code and visualize by ethnicity. So here you have eligible, panels, and random sample. So these bars, so when you look at the eligible and the random sample for Asian Pacific Islander, it's similar, right? But the panels jump very high. For Black or African American, eligible and random sample, they're very similar. But when we look at the panels, it decreased. For Caucasian, all of these are the same. Hispanic, also, the eligible and the random sample have the same height. The bar chart shows that the distribution of random sample resembles the eligible population, but the distribution of the panel does not. So this part is questionable. To assess whether this observation is particular to one random sample or more general, we can simulate multiple panels under the model of random selection and see what the simulation predicts for us. But we won't be able to look at thousands of bar charts like the one that we saw in previous slide. We need a statistic that helps us assess whether or not the model or random selection is supported by the data. Let us introduce a new statistic, the distance between two populations. We know how to measure how different two numbers are. You basically find the distance or the absolute value between those two numbers. Now, we have to quantify the distance between two distributions. For example, we have to measure the distance between the blue and gold distribution. Let's take a look at our visualization. What is the distance between these two? For this, we need to compute a quantity that we call the total variation distance between two distributions. The calculation is as an extensive of how we find the distance between two numbers. It's a little bit more complicated to fit into our class, but we're going to use the function to help us do the calculation. So let us augment the table with a column of differences between proportions. And as you can see, for ethnicity, eligible panels, the difference between these two, 26% minus 15% is 11%, 8% minus 18%, it gives you negative 10%. 54% minus 54%, you get 0%. 8% minus 12%, you get negative 4%, and so on. Take a look at the column difference and notice the sum of their entries is 0. So if I add these numbers together, 11% minus 10%, it gives you 1%. And if you add these two together, you get negative. So here you have 1% minus 1%, which is basically 0. The positive entries add up to 14%. So if you add all of these two numbers together, it becomes 14%, exactly canceling the total of negative entries, which is negative 14%. This is a numerical evidence of the fact that in the bar chart, the gold bars exceed the blue bars by exactly as much as the blue bars exceeds the gold. Well, we don't want this to be zero, so we have to take the absolute value difference. The proportion in each of the two column panels and eligible add up to 1 or 100%. And so the give and take between their entries must add up to 0. To avoid cancellation, we drop the negative sign by taking the absolute value. This gives us 2 times the total of the positive entries. Equivalently, 2 times the total of the negative entries with the sign removed. We don't need that doubling, so we're going to divide the sum by 2. Very good. So when you run this line of code, you can basically find the absolute difference between eligible and panels. Now, if you divide that by 2, you get about 14%. 0.14. What's the meaning of that? This quantity, 14% or 0.14, is the total variation distance or TVD between the distribution of ethnicities in the eligible juror population and the distribution in the panels. In general, the total variation distance between two distributions measures how close the distributions are. The larger the TVD, or total variation distance, the more difference the two distributions appear. In general, the total variation distance between two distributions measure how close the distributions are. The larger the TVD, the more different the two distributions appear. Here's a technical note for you. We could have obtained the same result by just adding the positive differences, but our method of including all the absolute differences eliminates the need to keep track of which differences are positive and which ones are negative. We'll use total variation distance between distributions as the statistic to simulate under the assumption of random selection. Large values of the distance will be evidence against the random selection. Now, if you take a look at the simulating the statistic under the model to see how TVD varies across random samples, we will simulate it repeatedly under the model of random selection from the eligible population. Let's organize our calculation. Since we are going to be computing total variation distance repeatedly, we'll first write a function that computes it for two given distributions. The function total underscore variation underscore distance takes two arrays containing the distributions to compare and returns the TVD between them. So let us define the function total variation distance, passing two arguments, and returns the sum of np dot absolute value of the difference between them divided by 2. So as we saw, the total variation distance in this case is 14%. Now in the cell below, we use the function to compute the TVD between the distributions of the eligible jurors and one random sample. Recall that eligible underscore population is an array containing the distribution of eligible jurors and that our sample size was 1,453. In the first line, we're going to use sample underscore proportions to generate random sample for the eligible population. In the next line, we're going to use total variation distance. So in our first run, it seems like the total variation distance is about 30%. What if I repeat this cell? If you rerun the cell a few times, you're going to get numbers that are quite close to 14%. For example, if I just run it one more time, I get 26%, 0.026. If I rerun this guy, again, I get 0.016. You are now ready to run a simulation to assess the model of random selection. So let us simulate one value of the statistic. In the same way that we start every simulation, let's define a function, one underscore simulated underscore TVD, that returns one simulated value of the total variation distance under the hypothesis of random selection. The code in the body of the definition is based on the cell above here in previous slide. So let us simulate one simulated value of the total variation distance between the distribution of a sample selected at random and the distribution of the eligible population. Now, simulating multiple values of the statistic. Let's see what's happening here. Now we can apply the familiar process using a for loop to create an array consisting of 5,000 such distances. So in this case, let us set TVDs and make the repetition to be 5,000. And for I in np.a range with repetition, which is 5,000, we're going to append TVDs to the TVDs that is calculated in your array. Now, how do you assess the model of random selection? In order to assess the model of random selection, we can use an empirical histogram of the simulated distance. It shows that if you draw 1,453 panelists at random from the pool of eligible candidates, then the distance between the distributions of the panelists and the eligible population is rarely more than 5%. The panels in the study, however, were not quite so similar to the eligible population. The total variation distance between the panels and the population was 14%, shown as a red dot that we saw on the horizontal axis. It is far from the tail of the histogram and doesn't look like as a typical distance between the distributions of random sample and the eligible population. So let us take a look at our line of code. They're going to create this histogram. On the horizontal line, you have the TVDs, and basically what you see is 14%, which is far away from the majority of the data which are located here on the left-hand side. The simulation shows that the composition of the panels in ACLU study is not consistent with the model of random selection. So our analysis supports the ACLU's conclusion that the panels were not representative of the population itself.